Alright, so this is going to be take two. I started doing it and I was kind of going haphazard and I didn't really like how it was flowing. So I think what I'm going to do, so I found an article that I thought was interesting today about, I don't really, is it a theory? Yeah, I guess they're considering it a theory. A new theory that bridges quantum mechanics and Einstein's shit. It's relativity. Theory of relativity. My brain just collapsed in on itself. My bad. Um, but essentially a new way of bridging these two, and I thought it was interesting. I don't really believe it. I think it's kind of explained. I'm gonna say loosey goosey. It's kind of explained really oddly, and I think that they're just kind of inserting a new thing that doesn't make sense into like to explain other things that also don't make sense, right? And I think it's just like you didn't really do anything but add an extra step, and it didn't really add anything. That's just kind of my opinion. Who knows? Maybe after the peer review, they're gonna be like, "Oh my God, yes, this is it. It explains everything. We finally figured out a theory to everything." Um, but I highly doubt it. But I think what I'm going to do is I'm going to go down through here and I'm going to actually read it like part by part and then just kind of give my take on it. Um, because the way I was doing it was just kind of like cherry picking things, and I don't think that the flow was right. Like I didn't really like how I was articulating things. So we're gonna try it this way, right? All right. So let's go ahead and switch here. There I am. I'm gonna go ahead and move. Oh, don't fight. Oh, don't fight with me, please. Thanks. All right, so we're going to set that there. All right, so this is the article. I'm going to link it on my channel like I typically do anytime I use something like this. Um, just so that you guys can go and read it and what have you. I mean, I'm going to read it pretty much verbatim. I'm pretty sure verbatim. But either way, so it the title is "What if the universe remembers everything? A new theory rewrites the rules of physics." I know, big catchy poppy headline. Not a fan of it, but it got me to click, I guess. So then, right here it says, "What if the universe remembers? A bold new framework proposes that space-time acts as a quantum memory." And then right here, I'll just read it. "For over 100 years, physics has rested on two foundational theories. Einstein's general relativity describes gravity as the curvature of space and time, while quantum mechanics governs the behavior of particles and fields." Now, I think that they just kind of, yeah, I guess it is the curvature of space and like, yes, I guess, but I think it's just kind of overgeneralizing. Um, I think that the general gist of quantum mechanics here is fine, though. They explained it better than I ever really could. I end up going way too in depth whenever I try to explain quantum mechanics. All right, and it says each theory is highly successful with its own domain within its own domain. Yet combining them leads to contradictions, particularly in relation to black holes, dark matter, dark energy, and the origins of the universe. Yeah, that's why no one's been able to figure it out. Because as soon as you start getting into the like hyper extremes of things, everything falls apart. Like all of our models, like we're just now starting to figure out like how to model things so that things make sense in like the very beginning of the universe. Like things are so extreme there that everything falls apart. Um General relativity falls apart, quantum mechanics falls apart. It all just doesn't make sense in those extremes. And it never has. Like the math just does not check out in any way. I believe I have seen earlier this year, maybe it was last year, that like we're starting to make headway, and I think it was mostly to the what is it's not is it JSAT? What is the newest satellite array? What is it called? No, it's not the NISAR. Um, well, probably after I'm done doing this, I'll go back and find it and just like insert it on the screen somewhere. Um, but we're just now starting to crack into those, right? We're just now starting to understand that and trying to piece together how those extremes can even exist in the universe or just exist at all in any point in time. All right. But here, it continues. My colleagues and I have been exploring a new way to bridge that divide. The idea is to treat information, not matter, not energy, not even space time itself, as the most fundamental ingredient of reality. We call this framework the quantum memory matrix. Uh, yeah, I'm just gonna keep reading. I'm not sold on the idea at all, but who knows? I could very easily be wrong. I mean, who am I? I'm just some guy literally in his spare bedroom talking about this. All right. So, title Space-time as discrete memory cells. At its core, at its core, it's a simple but powerful claim. Space-time is not smooth, but discrete, made of tiny cells, in quotes, which is what quantum mechanics suggests. Each cell can store a quantum imprint of every interaction, like the passage of a particle or even the influence of a force such as electromagnetism or nuclear reactions that pass through, or nuclear interactions, I'm sorry, that passes through. Each event leaves behind a tiny change in the local quantum state of the spacetime cell. In other words, the universe does not just evolve, it remembers. The story begins with the black hole information paradox. According to relativity, anything that falls into a black hole is gone forever. According to quantum theory, that is impossible. Information can never or cannot be destroyed. I don't like this last little bit right here. Um, According to relativity, anything that fall like the wording is just bad if you ask me. So it's just the way it's worded. According to relativity, anything that falls into the black hole is gone forever. And then it says in quantum theory that's impossible. Information it cannot ever be destroyed. So to me, the way that that reads is that uh, you read that and you go, oh, so anything that falls into a black hole is destroyed, but it can't be destroyed. No, things that fall into a black hole aren't destroyed. They just become part of a singularity. Anything that falls into the anything that passes the event horizon, like literally anything, like even the fastest thing in the known universe, which is a particle of light, a photon of light, if it passes the event horizon, it cannot escape. Nothing can escape that event horizon. And it doesn't get destroyed. Instead, it makes its way all the way to the center. Uh, there's many different theories on what exactly happens, but either way, it'll reach the center and become part of the singularity, which is where all matter that has entered the black hole is just in one super infinitely small and infinitely dense spot, right? And that's all it is. So it's still there. It wasn't destroyed, but yes, it is gone forever. Just I don't like that wording. Like it is irretrievable, but not exactly gone, right? Um, and yeah. So according to quantum theory, that's impossible. Information can never be destroyed, right? Yes and no. I will explain more because I believe down here. No. Okay. So with this, like, I believe what they were trying to get at here is so a black hole doesn't destroy it, but I believe that what they were trying to get at was Hawking radiation, which what Hawking radiation is so you also have to understand that there are constantly particles that are just kind of appearing everywhere all the time in the universe, right? So I'm gonna say like so there is matter and antimatter. I'm gonna just say like protons, all right, just kind of popping into existence. I don't actually think that they're that big. It might be quarks that are popping into existence, but I don't really remember. But essentially, you're having pairs of particles, one antimatter, one matter, just pop into existence whenever, wherever they want to at all times, right? But they pop in and then they just smash into each other and completely annihilate one another, like they were never here to begin with. Now, what Hawking radiation is, whenever one of those pairs pops up right on the edge of a black hole, now you have, like, if the antimatter falls in, now that antimatter particle will fall in and obliterate one particle of the singularity while the other one flies off into space. So now, because of that, now the black hole is one particle smaller, right? So slowly over time, and we're talking like an impossible to imagine or really calculate. Well, we can calculate it, but an impossible to actually perceive amount of time. These black holes will decay just one little particle at a time, one particle at a time, right? And I believe that that is what they were trying to get at, saying that, oh, black holes destroy the information that goes into it, or it destroys what falls into it. I believe that that's what they were talking about. Um, but like I said, I just don't like the wording because it's kind of like what's the word? There's ambiguity to it. Is it ambiguous? No, that's not a word. But there's ambiguity there that I don't think should be there. To me it sounds like snake oil salesman. Like, oh, we're gonna give you enough information that you think you know something, but you really don't know enough, right? And I'm not a fan. It leaves me with more questions than answers. Now they say QMM, which I already don't remember what that means. The quantum memory matrix offers a way out. As matter falls in, the surrounding space-time cells, which, if you remember, I'm sorry I went on a tangent, which is those cells are what makes up space-time, right? So like surrounding the black hole. Um, as matter falls into the black hole, the surrounding space-time cells record the imprint of what was there. When the black hole eventually evaporates, the information is not lost, it has already been written into spacetime's memory. So essentially, what it's saying is as the matter falls in, whenever it runs out of matter to fall in, and the Hawking radiation slowly radiates out, essentially that information that is coming out, well, the information that went in and I'm assuming is coming out because the Hawking, like, that's something that I'm now also not understanding, is because the Hawking radiation itself is radiation that would also be recorded. So now you're getting a double recording. Is that intentional? It might be. Um, but the information that went in has now been recorded onto these cells because it has interacted with these cells in some way to be like, hey, I was once here. Essentially, the way that I'm looking at this, to put it very basic, is these cells are essentially a log, right? Now, whenever I say a log, it's essentially like, look at like this water bottle, okay? So look at it as first it moves to the left, and then it moves forward, and then it moves down, and then it moves to the right, and then up, and then left, right? So it's here, and essentially the information they're saying is because it's moved all of those ways, you can reverse engineer it with math to put it back where it was originally, right? And that's the information that it is storing. That's the way I am taking it. Perhaps I am incorrect, but that is how I'm seeing it. Um, hold on. Yeah, so it's been written into spacetime's memory. This mechanism is captured mathematically by what we call the imprint operator. Okay. A reversible rule that makes information conservation work out. So like, but what is this? Like, what is it? Please explain this mechanism. Like, you're just all like, well, we made up yet another thing. So, and because we made this up, it works out. At first, we applied this to gravity, but then we ask, what about the other forces of nature? Okay, so at first you applied it to gravity, and how did that work out? Like, okay, what is that? That doesn't tell me anything. That is a nothing burger of a statement. um, maybe if I click on it, it'll actually tell me. Hold on, let me actually see here. I am curious. Ah, ooh, I'm gonna actually have to read through all of this. So after I'm done with this, I'm gonna actually have to go read through that and see if things make more sense, right? I should have probably done that to begin with in hindsight, but I'll be honest, I'm so used to hyperlinks on websites like this that just take me to other, what you call it? That just take me to other, like, written whatevers that, for the most part, have nothing to do with whatever I'm reading right now. So I didn't do that. That's my bad. That is on me. I will read that after I'm done with this. Um, At first we applied this to gravity, but then we asked, what about the other forces of nature? Turns out they fit the same picture. Oh, do they? How convenient. Did you make up something for them too? In our models, assuming that space-time cells exist, and the strong and weak nuclear forces which hold atomic nuclei together, also leave traces in space-time. Later, we extend the framework to electromagnetism. Although this paper is currently being peer-reviewed, thank you for telling me that, even a simple electric field changes the memory state of space-time cells. Okay, well, at least all information is being, recorded like you said it would. Explaining dark matter and dark energy. Now, some of this down in here I think is interesting to think about. I don't exactly believe it in this context, but I think it's very interesting to think about, and I'll bring that up then. That led us to a broader principle that we call the geometry information duality. In this view, the shape of space-time is influenced not just by mass and energy as Einstein taught us, but also by how quantum information is distributed, especially through entanglement. Okay, so I'm going to go into entanglement a little bit. Let me finish this paragraph though. Entanglement is a quantum feature in which two particles, for example, can be spookily connected, meaning that if you change the state of one, you automatically and immediately also change the other, even if it's light years away. Yes, they did explain this relatively well, but I just want to reiterate it. All right. So entanglement, essentially, what it is it is where two particles, no matter how distant they are, just like they said, if a state of one particle changes, one no matter how the other one that it's entangled with, no matter how far away, will also change. Such as if you put more energy into it and elevate what you call it? Oh, what's that called? Shit. My brain just entirely blanked on what it's called. Essentially, if you put more energy into it and you raise its energy level, you'll essentially do the same thing with the other one, right? That and same what you call it, vice versa. Um and again, it doesn't matter how far away it is, they don't care because essentially to themselves they're not one and the same, but like they're essentially right next to each other. Um the shift okay. And then it continues. The shift in perspective has dramatic consequences. In one study currently under peer review, we found that clumps of imprints behave just like dark matter. An unknown an unknown substance that makes up most of the matter in our universes. They cluster under gravity and explain the motion of galaxies which appear to orbit at unexpectedly high speeds without needing any exotic new particles. Okay, so now I'm going to talk about dark matter a little bit. Okay, so dark matter, essentially it is, our universe is comprised of, I think it's something like 90% of dark matter, it might be more, uh, to where essentially matter is what we interact with, the water bottles, the random little stuff around us. This is matter, right? Dark matter is essentially stuff that is invisible, right? It still has mass, but it's not interactable with. Um, Essentially the way I think about it is it's something that we just don't understand yet. And I'm pretty sure that that's how a lot of scientists look at it too. Is it's something that we don't understand, and I think it's just a gap in our knowledge. Dark matter, I'm pretty sure, is just kind of like a placeholder name, being all like, it's matter, but it's dark because we can't see it. We don't understand it. We have not shined a light on it yet to know what it is, but we know it's there because of how gravity affects it, right? To where it'll clump together, it'll form. I'm pretty sure it forms galaxies like dark matter galaxies or what have you. But like it's similar to like a black hole that like we can't see it, we can't interact with it. We know it's there because of how it interacts with matter and how it interacts with itself, but it's just we don't know, right? And dark energy is similar. I think I'll be able to get to that later. Um, it continues. In another, we showed how dark energy might emerge too. When space-time cells are saturated, they cannot record new, independent information. Instead, they contribute to a residual energy of space-time. Interestingly, this leftover contribution has the same mathematical form as the cosmological constant or dark energy, which is making the universe expand at an accelerated rate. Its size matches the observed dark energy that drives cosmic acceleration. Together, these results suggest that dark matter and dark energy may be two sides of the same informational coin. Okay, so dark energy, essentially what it is. So, I think most people know from school that the universe is infinitely expanding and it's getting faster as time progresses, right? So, that is what dark energy is. Essentially, it is the thing that keeps pushing the universe to get bigger. Um, and what they are saying here is essentially that this QMM, this quantum memory matrix that they came up with, can essentially describe both dark matter and dark energy. It's essentially saying that with with this QMM, with this quantum memory matrix, essentially the quantum memory matrix is dark matter. At least that is how I am. Yes, found that clumps of imprints of memory imprints on cells behave just like dark matter. So that is essentially to me saying that this memory in the cells now has mass, which I don't like that. That doesn't make any sense to me. How can, well, I guess dark matter in and of itself, how can nothing have mass? That's dark matter. So this is really not any different. It's just the same whatever. Um But either way, so essentially it's saying that the memory imprinted on the universe has mass to it, which then causes gravity to clump it together, and then it forms galaxies and everything, and pulls on everything else. That's okay. It seems a bit far to me. And then it's also saying that the same information, um, essentially. All right, so in another, we showed that dark energy might emerge too. Space-time cells are saturated. They cannot record new independent information. Instead, they contribute to the residual energy of space-time. Interestingly, this leftover contribution has the same mathematical form as a okay. So essentially what it's saying is whenever space-time, so whenever there's so much information in these cells that it can no longer record new information, it is equal to dark energy. It is equal to what is known as the cosmological constant, or the dark energy that is constantly pushing the universe forward, right? Which is constantly pushing the universe to expand infinitely and get faster. Um, and then it says, yeah, said the size matches the observed dark energy and drives the cosmic acceleration. So, and then okay, and then essentially they're saying that this information, uh, that they are proposing is it has weight and is able to push the cosmological constant. That just doesn't seem right to me, because that means that dark energy and dark matter are the same thing doing two different things, which not the worst thing that I've heard in my life. Like, but they're two different things serving two entirely different purposes. And then also comparing it to like the two sides of the same coin, like it's not really. If you ask me, it's not really. I think later in this paper, the way that they explain like the next title is a cyclical universe with a question mark, right? And I think that that explains an informational coin better than these two subjects do. But that's just me. All right. All right. So it says a cyclical universe, but if spacetime has finite memory, what happens when it fills up? Our latest cosmological paper, accepted for publication in the Journal of Cosmology and astroparticle physics, points to a cyclic universe. Yeah, points to a cyclic universe being born and dying over and over. Each cycle of expansion and contraction deposits more entropy, a measure of disorder, into the ledger. When the bound is reached, the universe bounces into a new cycle. Okay. So this is something that I've read recently to where I can't remember the name of it because like there's the heat death of the universe, which is whenever everything expands and separates so much that nothing can happen anymore because every single particle that ever exists is so far away that it'll never interact in any meaningful way again. Um and there was another one, I don't remember what it's called, to where there is a theory to where once it gets to that state, the universe will actually contract, and it'll be called it's called the big squeeze, I'm pretty sure, to where it'll go from there's absolutely nothing happening to where essentially the universe will reverse and then contract until everything squeezes into one finite point and then it will explode again in another big bang, right? that's that is the first part of what they're talking about, right? That is the thing that was actually put in the Journal of Cosmology and Astroparticle Physics. Is that theory, right? Is that thought, right? Um, but they're trying to hijack it at least somewhat. Um, so it continues. Reaching the bound means space-time's information capacity, entropy, in quotes, or yeah, in quotes, is maxed out. At that point, contraction cannot continue smoothly. The equations show that instead of collapsing to a singularity, like like what I mentioned before, uh, into a singularity, the stored entropy drives a reversal, leading to a new phase of expansion. This is what they describe as a bounce. So essentially, what they're purporting is instead of it being it goes until there's a heat death essentially, and then it reverses into a big squeeze, and then everything collapses into a singularity, and then there's a new big bang. What they're saying is what it does instead is it will reach a certain point to where there's so much information that it'll then contract some until essentially information or it'll contract some and then it can essentially store more information. Like it'll contract some, essentially like squeeze some of the information together, or maybe destroy it. I don't know. They didn't explain it here. And then because it can store more information, it will begin expanding again, and that is what they call a bounce. Um, and then it continues here, a finite informational age. By comparing the model to observational data, we estimate that the universe has already gone through 3 or 4 cycles of expansion and contraction, or as they put it, bounces. They've went through 3 or 4 cycles of bounces, with fewer than 10 remaining. After the remaining cycles are completed, the informational capacity of spacetime would be fully saturated. At that point, no further bounces can occur. Instead, the universe would enter a final phase of slowing expansion. So essentially, what they're saying is that there is a certain amount of bounces that'll happen until uh, the cells of the universe are so saturated with information that it can't squeeze anymore. So essentially, the way I'm thinking of this, right, is that it gets so full that it contracts, that like the bounces, it contracts just to squeeze information together so that it can get a little more mileage out of it. And then it'll hit that saturation point and then it'll bounce and squeeze some more so it can squeeze some more information into the cells. And then it'll go out and then it'll bounce again. And each time it'll be bouncing a little bit less. Well, a little bit in these kind of terms, it's like a lot less, but each time it'll be less until eventually the final bounce will happen and then it just won't be able to bounce again. So then it'll just keep expanding at a slower and slower rate. Um, that makes the true informational age of the cosmos to be about 62 billion years, not just the 13.8 billion years of our current expansion. So essentially, what they're saying is the 13.8 billion years that scientists are saying that's how old our universe is. These people are saying that no, 13.8 billion years is just the current age of our current expansion, right? There have been some before, and there will be some after. This is just the current age of our expansion. Um, and the full life of all of it. So true information, cosmos. So now, with them saying it's 62 billion years, does that mean that it is currently 62 billion years old, and the age of our current expansion is 13.8 billion years old, and then there's still time left? Or are they saying that 62 billion years is the whole life cycle of all of it? I think that they're saying that the current age is 62 billion years, and our current cycle is just 13.8. Either way, it continues. So far, this might sound purely theoretical, but we have already tested parts of QMM on today's quantum computers. We treated qubits, the basic units of quantum computers, as tiny space-time cells using imprint and retrieval protocols. Based on the QMM equations, we recovered the original quantum states with over 90% accuracy. Essentially, what they're just saying is they took their QMM equations, plugged them into current what you call it, current quantum computers, and they're able to return the original protocols. Hold on. Using imprint and retrieval protocols based on recovered the original quantum states with over 90% accuracy. So essentially what they're saying is they set them at some certain amount or what have you. I'm just going to say amount for lack of a better term. They sent each of them to a certain amount and then ran them through a bunch of random whatevers and then used the QMM equations to essentially reverse engineer the information uh, of the what you call it, of the qubits and the quantum computers, and 90% of them came back as what they originally set them as. And I mean, that's neat, that's cool, but to me, it's just all like, all right, so you found a way to accurately reverse engineer where the qubits started. Like, where my brain is at is all like, you came up with this whole theory of the universe, but in practicality, like, I feel like this is actually all you were really doing. Is just trying to reverse engineer qubits, and then you tried to blow it up to be bigger than it seems. Maybe I'm just being an ignorant asshole, but that's just kind of what I'm seeing. It's just being all like, this is neat, like, this is cool, actually. Like, good on you for doing that. That's awesome. Um, but at the same time, I feel like you're just reaching for more. I don't know. Either way, I think I'm just being a dick. Just call me a dick. That's fine. But I don't like this. This is cool. I don't really vibe with the rest of this, and I do want to go back to this, like the cyclical universe. I like this. I like the thought of this, but not in our universe or our current age. I feel like in some sort of a like in some sort of fiction, this would be neat, right? Just like if this is how a universe worked in fiction, it would be super neat. Whereas if a universe kind of like it expanded and then it would stop and then contract just some and then keep going out until eventually it would just stop contracting, and each time you did that essentially it would just like squeeze the matter a little bit closer together or what have you, and it would so like there's the current issue with like the galaxies we can see right now. In billions of years we won't be able to see them because how so gravity will bring our superclusters of like the galaxies that we're closest to, like the galaxies in our home group, will actually bring them to merge with us, right? But the ones that are outside of that home group where gravity isn't strong enough to pull them towards us, um the not dark matter, dark energy is actually pushing them away. Like, because how the universe is expanding isn't just at the edges, it's everywhere all of the time. So the expansion of the universe is actually pushing them away from us at such speeds that eventually we won't be able to see them anymore, right? So it'd be super neat uh if in fiction, like the bounces would actually squeeze those galaxies back towards each other, so that life had more chance to, reach each other before the final saturation, to where either it just continues to expand at a very slow rate, or if maybe it just stops expanding altogether. I think that that is just a super interesting concept, right? I like that, but for our universe, I'm not a fan, right? But also at the same time, how they're reporting this, it's not working exactly how I just said it. Um, but either way, so like I like it as a concept, but I don't exactly like it as it is now. All right, and then this is on the practical tests on quantum computers. And this is the last little bit. I'm just gonna read it. Honestly, like I was saying before, like it this is interesting and I like it, but I think that this is just what they should have done with it, not try to turn it into a theory of everything, right? Cuz I think that this is where it ends. Um it's just how it's really good for like quantum computers, like being able to backtrack or backsource where a qubit was at some point in time, right? 90% accuracy is good, but it's still not. I don't want to undersell this. 90% is really fucking good, but that 10% is also massive, right? uh 10% inaccuracy is just like, it doesn't seem like that bad until you put it on a massive scale, and then you're thinking, 10 out of 100 people, that's a lot. um but I will just continue reading this so that I can finish reading this, and I'll go read the other thing, and I'll decide whether or not I want to record my thoughts on that and then upload it after this. I'll see here. But either way, practical tests on quantum computers. This showed us two things. First, that the imprint operator works on real quantum systems. That the imprint operator, yep, works on real quantum systems. The operator being the thing that they made up. Yep. One of the things they made up. Works on real quantum systems. Second, it has practical benefits. By combining imprinting with conventional error correction codes, we significantly reduce the logical errors. That means QMM might not only explain the cosmos, but also help us build better quantum computers at the same time. That's probably where you should just stop. Quit while you're ahead. Um, QMM reframes the universe as both a cosmic memory bank and a quantum computer. Okay, so now the universe is a quantum computer too, boys. Every event, every force, every particle leaves an imprint that shapes the evolution of the cosmos. It ties together some of the deepest puzzles in physics, from the information paradox to dark matter and dark energy, from cosmic cycles to the arrow of time. You didn't mention time anywhere, motherfucker. You didn't. This is the first you're mentioning time at all in this article. Don't you pull that bullshit on me. Try it with someone else. And it does not. And it does so in a way that can already be simulated and tested in the lab. Whether QMM proves to be the final word or a stepping stone, it opens a startling possibility. The universe may not only be geometry and energy, but it is also memory. And in that memory, every moment of cosmic history may still be written. It's a pretty good send off, I'll be honest. But I do like that they acknowledge that, whether it's the final word or just a stepping stone, I would be happy with it being a footnote, right? Like if I were to have made this, which obviously I'm not smart enough to, but if I were to make this, I'd be a-okay with it being a stepping stone. But that's just kind of how I am in general. Like I just want to get people thinking, right? I want to get people heading in the right direction. That's all that really matters to me, right? I'm gonna go ahead and put this back over here and put this. And in all honesty, that's just kind of how I like to think, right? Even if I don't give you the solution, if I get your mind on the right track to find the right solution, I'm happy. You finding the correct solution is what matters, right? It doesn't really matter how you got there, or how long it took, just as long as you got there, right? So I'm going to in this video, like this part of the video here, I'm gonna go read over that and see if it's worth going over. Um, and if it is, you'll see me again right now. If not, I will see you next time.